Hi, I'm back with lecture 14. I forgot to put the number of lecture at the front, but we are at the 14th class for this course already, so we are left with just 2 or 3 more, including this one. Hooray! Alright, so for the topic for today is hypothesis testing with one sample. So you can guess that tomorrow, next week, we are going to learn about hypothesis testing for 2 samples, but for now just one. So this is gonna be a new topic, but still related to what we have done so far. So what we have done so far here, so we study all kinds of distributions, and the most famous one and the most useful one is the normal distribution. And I'm pretty sure you are sick with this bell curve already because I have drawn this every time, but we need to know it, right? So we use math to construct this normal curve, normal distribution, and now we are asking what can we do about that? What kind of information we can extract from this curve and use it to predict or to conclude something about the real world situation. So this one is ideal, but like in the real world we cannot get a continuous distribution. We only get a few samples, maybe 100, 1,000, or however many you can do. And from that small set of samples, what can we say about the actual population? And so we have something is wrong with my. Give me a moment. Oh, never mind. Okay, we have this world, the sample world, where we get an actual number, and we have the population. But this thing is obscure. We don't know about it at all. So we are trying to infer. Maybe infer from this sample. So let's say we collect a sample from 30 students and we get a mean of some amount. Then what can we say about the actual population of maybe 1,000, 10,000 students in the whole college? Right. So last time we did one thing, right, that we call the confidence interval. Right. So that one was kind of intuitive enough, right? So we get a sample, we get a number from the sample, right, x bar. Maybe we get 30, or let's use different number. Let's say maybe we get 100, or let's just use average height. So let's say the average height is 160 centimeters. Yeah, that's from the sample. So since there is no way we can get the right population mean, then at best we can say it should be between this number 160 plus or minus something, maybe plus or minus 5, or let's say 3. Maybe it's plus 3 or minus 3, right? Maybe that's the best we can do. We can narrow it down and say, okay, we are only 90. We have the confidence level. Right? We are 95% sure that the number will fall into this range. Right, so that's the thing we studied last time for the confidence interval. This time we are going to say a little bit more, or maybe a lot more, about the population themselves, right? And this is what we call the hypothesis testing. So let's get into the topic. So we have this chart last time, right? So we first get a sample, of course, because without that information we cannot say anything. Right? We get a sample, and we get some information. We get graphs, we get the measurement, like the mu, the sigma, the p, or whatever. Yeah. And then we went to this path, right? We get from that number, we use probability to get some estimation or confidence interval. These two are the same concept, just with different wording, and then we decide on something. So today and next week we are going to learn about the other part here, which is the hypothesis testing. So let's see what we. So okay, yeah. So we are just a brief outline for this lecture and the next one. So for this lecture we are going to learn 3 things. Right. If anything, I hope you at least at the end of the lecture you can explain in your own word what these 3 things are. Like what is the null hypothesis, what is the type 1 and type 2 errors, and what is the p-value. Right. You don't have to memorize all the formulas. At least at the end, I want you to be able to explain what these 3 things are. And hopefully, again, if I ask you this question again next week, I hope you can explain or at least recall the concept, the basic concept, like the high level explanation of these 3 words. Right. But also you are supposed to know how to compute something out of this one for the test. But just to have a basic understanding of the statistics for this course. These are the 3 concepts. So let's start with the null hypothesis. So there's a crash course here. You can click on the link. Either actually after I finish the first part, like this one is actually the condensed version of the first part of this lecture. We should be like in the first clips. Because you can see there are 2 words that we haven't learned yet, like the p-values and the hypothesis. So yeah, actually I should have put that at the end, or maybe I'm not sure how this is work, but okay, let's just click on the link and watch this clip. If I don't forget, I will put on the as a card in YouTube, so you can immediately click on that link. Right. So take a brief look at better animation and explanation, and come back to how can we compute all its values. Okay. So let's get through the definition first. So the null hypothesis is an assertion about something, about the value of the population parameter. So recall from last time we 2 lectures ago, right? The population parameter. So the main theme here is we have something from a sample. We have a different thing for the whole population. Okay. So we can find the average from the sample. We can find the proportion from the sample. We can find a standard. We can find the variance for the sample. But we are trying to use this information, this limited information, to conclude something about the actual parameters or the actual value. These 3 values. So the values on the right hand side here is the population parameters, like mu, p, and p, mu, and sigma. So we are trying to make an assertion. We are trying to assume something about the right column, which we will never get. We will never know what it actually is. But we are trying to make a guess, an intelligent guess on what it should be, right? So the guess should be of the form that. Yeah. So first of all, the h0 or h null, it's just a name. Right? We're gonna have a full statement as in the sentence, which is the statement P. But we are gonna abbreviate that and refer to that statement as h null. Okay, and we will see in a moment what kind of statement it is. So, for example, we may assume that Right? This is true. We don't know yet, but we have to assume something at first. So here we are assuming that mu is at least 100. We don't know. We know nothing about mu. We don't know nothing about the population mean, but we can assert that mu is at least 100. Okay, so we believe it is 100 at least. It might be 200, 300, or 101, or whatever. We don't know. Yeah. So this is what we believe at first. Right? We believe that this is true. Right. So we have something that we believe is true. We also have to have the opposite, which is the alternative hypothesis, which is the opposite of what we just say. It is the negation, which is a mathematical term for statements. Right? So if we believe that mu is at least 100, then the opposite, which is when the hypothesis is false, is that mu is at most 100. And so it's the other way around. If we believe that mu is at least that number, then the opposite, or H1, the alternative hypothesis is that H is less than 100. Right, simple enough. And this you can use both mathematical terms, or you can just put in the sentence whatever you find more convenient. So right, so let's look at this example. So suppose that there is an automatic bottling machine that fills 2 little bottles with cola. So the company claims that the average for each bottle contains at least 2,000 centimeter cubes, or 2 liters of sodas. So the company, somebody else claims that, maybe it's true or it's not true, but they claim that the average is 2,000. So if you want to just write that as a full sentence, you can do that. You can say H0, or the null hypothesis is that the average each bottle, the average amount of soda is at least 2 liters or 2 cm cube. Okay. So you can put that in the whole sentence there. And for that to be a statement, it has to be either true or false. Remember from the what's the topics? The logic from last semester. Sorry, gotta close my window. Okay. So we claim that it is at least 2,000. Okay, so it can be either true or false. Maybe it's actually at least. Maybe it's less than that. We don't know yet. But that is a statement. But if you want to convert that into more mathematical terms, we write it as H0 and then colon. Right? And then we say that mu, or the average, is at least or greater than or equals to 2,000. Right? So you can either write the whole sentence there, or you can just abbreviate and make it a mathematical statement. Okay. And then you can see that the second statement is a lot easier to read or to look at. Okay, so that's the null hypothesis. This is something that we believe to be true. The opposite, or the alternative hypothesis, which we express that as an H1, is the opposite. So in the math term, maybe that is easier, right? If you think it is at least 2,000, the opposite of that is that it is at most not including. It is less than 2000. And the opposite of that is the other way around. Or if you express that as a sentence, and you say, okay, the average amount of soda is less than 2000. It is either less or greater or equals. So the way we put these two statements this way is that we know for sure that exactly one of these statements will be true. Okay, exactly one of these statements will be true. If our original hypothesis, our null hypothesis is true, then the opposite or the alternative hypothesis will be false. If, on the other hand, the null hypothesis is false, then we can conclude that the alternative hypothesis, H1 here, is true. Right, so there's only one way. Right? Either it's true or false, or this is false or true. The other one is true. Okay. So we believe something is true as H now. Right? If that is not true, then the other one, the alternative, will be true instead. Or here, if you want to test whether the mean GPA of students in American colleges is different from 2.0 out of 4.0. Okay. And again, this one use the American colleges because this is an American textbook. Right. So what it means? It means is that we believe, right, that the actual average, the actual mean, is at least is 2.0. Right. So we could let the null hypothesis, right? Okay, let's look at the keyword. What we are trying to see here, we are looking at the mean, right? So the mean corresponds to the mean, the population mean. Okay. We believe that it is 2.0. So we can write it this way. Okay. So now our null hypothesis is that the mean GPA of our students in American colleges is 2 or 2.0 if you want, so that it matches the original statement. Right. So if we believe that it is exactly 2.0, then what would be the opposite? The opposite would be that it is not 2.0. So this one is different from the previous one. Right? If we have a greater than or equal sign, right, the opposite would be less than sign. If we have a less than or equal sign, right, the opposite of that will be greater sign. Okay, but for the equal sign, the opposite is not equal. It's as simple as that. One thing to know is that, like, for some reason, there is no such notation. We don't just use that as like just like the way we use equal or not equal. Right? We have greater than. We don't put not greater than. Right? The opposite of that is actually less than or equals to. So that's somehow not intuitive. But anyway, okay. So sample 4, that's the same one. That's what a mistake for my part. But let's forget about it. So, oh wait, I think I forgot something. Yeah. Oh, but because since the null hypothesis is about the population parameters, it could be either about the population proportion P, or about the population standard deviation sigma. It can be one of these three things. So it could be something like that. Maybe I believe that P is greater than 0.4. Maybe I believe that sigma is less than or equals to 1.5, or sort of thing. So it's one of these three parameters, mu, P, or sigma. right? And one of these three sides, actually there is like some minor nitpick that for the null hypothesis we only use equals, less than equals, or greater than or equals. For some reason we don't use less than or greater than. We only use this three. So mathematically you can only make 9 different types of statements, right? You can claim that mu is equals to something. You can claim that mu is less than or equals to something, or mu is greater than or equals to something. You can claim that p is exactly equal to something, p is less than or equal to something, or p is greater or equal to something, and less than this sigma. And so it's only these three parameters and these three sides. So the question you may ask first is, why do we have to assume this thing, right? And the quick answer is because we don't know yet. We don't know, and there is no way to determine exactly what these three values are. So we can only make some assumption. Because actually we could measure the whole thing. We could measure the whole population, right, and get these exact values of mu, p, and sigma. But of course, because it is impossible, right, or almost. Yeah. So we can only get the alternative, which are the x bar, the p hat, and s. Okay. And then since this is not going to exactly match the exact value, then we can only state our confidence. Okay, we have some amount of confidence. We are not going to be 100% sure. So we have to adjust how confident we want to be for these values. Okay. And next, the concept is that we, in our life, professional and personal life, we often have to make the accept or reject type of decision based on incomplete data. So maybe we look at, I don't know, we look at a box of balls, right? We cannot get the whole box, right? So we may sample get some amount of balls out, okay? And then we have to decide if we want to buy the whole box or not, something like that. Okay, think of like maybe a box of apples. Maybe that's more realistic, right? So you have a box of apples. Some of them are good, some of them are bad. You don't know the whole thing. There's no way to determine the whole box, because that will take some time, right? So the only thing you can do is you take some apples of this box, okay, and you count how many of them are good or bad. Now, how many of them are large or small, right? And based on that small decision, you have to decide whether you want to buy the whole box, right, or not. Okay. You can think of it as like get an apple from this farm. I just say that's like, I don't know, farm A. Sorry for being not too creative. Right. You go to farm A and they give you this box of apples, and you take some of them out, and you have to decide whether you want to buy more apple boxes from this farm. Right. So since maybe you want to buy millions of apples, there is no way you can get every single one of them. So you have to get a random box and look at them and determine if this farm produce good enough quality apples for you, right? If you believe they are good people producing good stuff, right, you decide to buy from them. You place an order and maybe buy every month, every year, right? Or if not, if you think, oh, they have too many bad apples in this box, in this one box, so you decide to not buy from them for now, for forever, maybe, and then you move on to farm B, farm C, and so on. So it is kind of like the decision we make from incomplete data. Okay. And because as long as it is based on just not full evidence, right? There's going to be some error. Right? It is possible that when you decide to buy from this farm, they turn out to be bad farm. Let's just say if they are good farms, right, you decide to buy from them, and you get good apples every week, you are happy. Right? Maybe they are bad. You look at 2 boxes and they seem pretty good, but then once you press an order, they send you 100 boxes. Like half of them are bad. That's possible. Maybe they trick you. Maybe you didn't make a good decision, right? And if you decide to not buy from them, right? And then again, there are going to be 2 scenarios. Right? Maybe you look at 2 boxes, and it doesn't meet your expectation. But it turns out that they are a good farm. They have a good farm. Like maybe out of 100, only those 2 boxes are bad. Like the other 98 boxes are good. But you happen to get 2 bad boxes, and then you decide, okay, this farm is bad. We are not going to come here again. That's possible. That's gonna be unfortunate. Right? Oh, sorry. If you buy, yeah, you are happy with that. Right? If you buy from them, they are bad. You are unhappy. If you don't buy from them and then they try to be bad, maybe out of 100, 95% of them are bad, and you get bad ones, so you can correctly judge the apples from the whole farm. In this case, you would be happy with that. Right? And on the other hand, if they are good farm, but you decide to pass on them, you decide to not buy from them and choose a different farm instead, then that again will be bad for you. Right? Oh, by the way, this is not math. Right? This is just like common sense and trying to formulate our natural thought process here. So these are the scenarios you will encounter when you decide, when you make a decision on something. Right? Maybe you're right, maybe you're wrong. So let's look at this like kind of a standard example here, pregnancy test. So someone goes to a hospital, yeah, and then the doctor, maybe, what's the word of that? The doctor looks at the patient and derives at some conclusion. So maybe the doctor suspects that the patient is pregnant. Right, that's pretty common. Right. This is the thing that the doctor believes to be true. Right, and then there of course there are 4 scenarios. Let's see if I have. Oh, it should be up there. There are 4 scenarios, right? The first scenario is when, let's write it here. Is this going to let's use a table here. No. Alright, okay, there are gonna be scenarios here. Okay. So the hypothesis, the null hypothesis, could be either true or false. Okay. So that's the axis, the column is for the actual statement, and the rows now it's gonna be about our decision. We may want to belief. Let's just do the word belief, right? And that's too small. Let me use it as just the B, belief. Right? We made the belief H0. Right? We believe that the patient is pregnant. Right? If we believe the patient is pregnant and she is actually pregnant, then we are happy with our decision. Right? Because our decision agrees with the actual situation. If we believe that the patient is pregnant, but he or she is not, then we make a false assumption in the first place, and maybe we give them medicines that they shouldn't have taken in the first place. That would be the second scenario here. So we believe that the patient is pregnant, but actually he or she is not. And in this picture, it is obvious that he is not pregnant. That means we are wrong. So that's one scenario here. And the second one is that we reject the possibility that the patient is pregnant. Maybe it comes from different way. Maybe the other doctor sets up the hypothesis. Maybe we didn't do it ourselves. Someone else did it for us. And then we have to test whether it is true or false. If we decide to reject, right, and the patient is not pregnant, then in this scenario we are happy with the result. Right. And on the other hand, we may reject, right, while the patient is actually pregnant, then that we would not be happy with that scenario, right, which is the type 1 error here. This is when we reject, but she is actually pregnant. Right. In this case, we may dismiss the patient. She goes home, and then maybe, I don't know, something bad might happen. Right. So of course we don't want this scenarios to happen. Right. But how can we do that? How can we make sure that these two cases would be less likely to happen? It depends on how we make a decision. If we have some good set of policies or some good procedure to make a decision, then we can be pretty sure that we will make good decisions most of the time. I'm saying most of the time because, of course, there is something. It is possible to get an error. We might be wrong. Maybe even like 0.1%, 0.01%, and that still happens. But we are trying to do our best to minimize these two cases. And so that's the goal here. We have to minimize the possibilities of these two cases. So before we move on, let's take a look at two more examples here. So this should be pretty familiar for all of you if you are in Bangkok. If you watch this from somewhere else, hi, I'm from Bangkok. I'm teaching math in Thai University. But anyway, so maybe someone else, like the government or your friends or your family or someone on the internet thinks he is right, and he say, wow, you see, I believe that water spray helps reducing the level of PM 2.5. And of course, we just pour our water sprays everywhere, right? Someone believes that. Then let's take a look at the 4 scenarios here, right? The hypothesis itself, the null hypothesis itself, might be true or false, right? Either way. And for us, for people who are in charge of government or in charge of making a good policy, or just anyone on the internet, right, might decide to believe or reject the word here is we use the word reject, and believe, which means we do not reject, right? We don't use the word accept here, right? Because we assume that this is true in the first place. If this one is already true, then we don't accept it again, right? We believe it, but we don't accept it because we have accepted already. We have already accepted that this one is true, so we don't have to accept again. We can just believe it, just continue what we are assuming in the first place. That's why we use the word do not reject. We don't accept. We just do not reject. It's still true. It's just true. There, nothing has changed. So if this is true, if it actually helps, right? And then we do not reject. What do we do here? If we believe it's true, if it's true, and we believe it's true, right? In that case, we would carry out the procedure. Right? We would actually use water spray to try to help to reduce the level of PM2.5. Right? In that case, we will be happy, right? Because we make no error. We use the spray, and it actually helps decrease the level. Right? We are happy with that. On the other hand, if this happens to be false, and we reject, right? We think, okay, that doesn't help. There's no way it can help, and we reject that. It means we don't do anything about it, right? Because if it's false, then what's the point of doing it in the first place? Right? In that case, if we happen to be correct, then we will be in this scenario in the bottom right. Right? There's no error here. It is false, and we reject it. That means we save money. We save money. We save resources. We can spend our resources to do something else, right? Trying to help reducing the level of PM2.5. On the other hand, right, of course there are two different scenarios here. If we do not reject, if we believe it does help, but in fact it doesn't, right? If it's false, that means we believe, so we use the water spray, right? We spend money, we spend millions, 10 millions, right, to spray water all over the place, but it turns out to be false. That means what happens here is that we waste water, right? So we do something, but it doesn't yield any good result. So we waste water, and we don't want that to happen, of course. And on the other hand, if we do not believe, we think, oh, that's fake news, that's false, there's no way it can be true, but it turns out to be true. What happens here is we lose the opportunity to actually reduce the level of PM2.5. Maybe we don't believe and we do something else, so we lose the nice opportunity to actually make a difference, to actually help people. So these are kind of possible scenarios here, okay? Based on two inputs, right? Based on first the hypothesis in the first place, and also based on our decision. Okay? This is true if the hypothesis is true and we reject. If it's true but we do not reject. If it's false but we reject. And if it's false but we do not reject it, what would happen there? And that's another hypothesis. So let's pause the video, read that, and try to make the table for yourself. Right, so suppose the now hypothesis is that H0, the victim of an automobile accident, is alive when he arrives at the emergency room of a hospital. That's kind of long statement, but the keyword here is like alive. That's the keyword. Whether the victim is alive or not, Yeah, so let's list all the possible scenarios here. If you haven't paused the video, please do so now, before I give you a solution here. If not, then of course we can do it. I suggest you do it. Give it 2 minutes, draw a table, list all the scenarios here, and then check the answer afterward. That's better for learning. So anyway, let's fill in the entries. Right. That shouldn't be red. So, is it possible that it is true? Right. That's true or false? Right. If it's true, then that means he's alive. How do you say alive? I don't know. He's alive. Maybe he's still in jail. He loses his consciousness, but he's still alive. Okay. Or he might be dead already by the time that he's at the hospital. Right. As a doctor or as I don't know, healthcare workers, right? Maybe you don't have enough tools or enough equipment to test if he is alive or not. Maybe you can test, but you are not sure about the result, right? So you can only make two decision, right? So you do not reject, or you reject that idea. Okay. And as a rule of thumb, like it should be common practice that we assume that he or she is alive in the first place, right? Because that makes more sense. If we assume everyone is dead, then we just kill everyone and let them die. That would be too sad, right? So we have to assume that they are alive in the first place, right? And then after some experiment or some surgery operations or whatever, then we have to decide whether we were correct or not, right? So if he is alive and we do not reject, which means we treat him, we put him into a bed, perform surgeons or whatever, right? And then he would survive. That will be like the best scenario, right? Because that's the result. Then we have hospital here to treat people, so we should be happy that they survive. Right? And on the other hand, if he's dead and we reject, which means we do not believe that he is alive, right? And in this case, we make a correct decision. If you think he's dead, maybe his head is not attached to his neck or whatever, right? Then we can say, okay, he's dead, so let's move his body or whatever to somewhere else, right? That means we make a correct judgment, and of course we save resources, right? Both in terms of medical resources and time for doctors, right? Because maybe the hospital has limited number of beds and doctors and whatever. Right? If we waste too much resources on the case that we shouldn't have to, then we might miss an opportunity to treat a good patient. Okay. So we have to move those people out, or those corpse out. On the other hand, we may commit some error. Right? Maybe we reject. We don't believe he's alive. He's like on the bed, but we don't believe he's alive. So we move him to, I don't know, to, what's the word for that? Catacomb? I don't know what's the word for it. Right. So let's put him into the cold room or something, right? Which means he's now dead. And of course that's bad, right? We should have threatened him, but now he's dead because we made incorrect judgment. Right, so of course we are not gonna be happy with that scenarios, right? And for the last one, if we do not reject, or if we still believe that he's alive when he's already dead. So let's say again, if there is no head or the neck, and we still try to resuscitate, I think that's the word, by trying to get him back to life, right? Put all the surgeons, all the equipment, into the room, and try our best for hours to give his back life, right? And then we're gonna fail because he's already dead. So again, in this case, we are gonna waste resources, and we shouldn't have to. Sorry. Right, so again, we would be unhappy with this result here. So these are about all the possible scenarios here, and of course, our goal as a decision maker is to minimize this case and that case. Okay. Minimize means we want these two cases to be very low chance, because we cannot make it. We cannot be 100% sure, right? Maybe we want this to be 95% correct, and 5% wrong, or maybe we want to be 99.9% correct, and there is a small chance that we could be wrong. So our goal is to juggle with these numbers and see what we can do. So here are two remarks. Right? The first question is, of course, can we reduce the type 1 error, the false positive error, to be 0? And the answer is yes. Let's go back to the table. We want the false positive case to be 0. Right? So that means if we want this chance to be 0, right? That means we have to never reject, right? If the type 1 0 chance, right? That means we never reject. If we never reject, then there's no, we are not going to get to this scenario, right? We are going to get to only the top row, like not the bottom row. We can, of course, say we always accept, we never reject, right? But then you can see immediately that that's kind of like bad practice, or just say it's stupid, right? If we treat every single one that comes to the hospital, right? Even if he's dead, he's like obviously dead. Then, of course, if we're trying to avoid the scenario on the bottom left, right, then we would be faced with errors in the top right column instead, top right entry instead, right? If we are too afraid of type 1 error, we would increase the possibility of type 2 errors. But that means we have to waste all the resources to try to treat every single person, whether dead or alive, right? That would be not practical. So that means we never reject, right? But then we get type 2 errors instead, right? That we increase. On the other hand, can we reduce the probability of type 2 error, the false negative, on the top right column? So let's say we do not want to waste resource. Like we want to avoid this scenario here. What do we do here? Again, if we don't want to get to here, right, we can just ignore the top row altogether. Now that means what we do here, yes, we can reduce it, but that means we have to always reject. Right? what it means is whoever comes here, we are gonna assume that they are all dead. Like whatever person or corpse comes to our hospital, we are gonna send them all to the cold room and let them sleep there forever. Like we can always reject, yeah, sure, but that means we gonna see this type 1 error instead. Like we're gonna have more dead people, so type 1 error is gonna increase, right? Obviously. So this means that we cannot reduce both either of them, right? If one of them is small, then the other one is gonna be big. If the other one is small, then the other one is gonna be big. Like these two values here are correlated to each other, right? So in practice, in reality, we can only trying to get small errors for both types. We cannot get 0 on both or on any of them. I mean we can, but it's gonna be foolish. So we can only settle for small values here for both type 1 and type 2 errors. Maybe we want that to have maybe 1% and 1%, something like that. Right? That is still practical. Or if in this in the previous example about the dead people, right? We don't want people to be dead, right? Let's say we have enough resources and we don't want to see dead people. We might settle for something like 0.01% here, right? But that means that's gonna increase the error on the other code in the other entry, right? Maybe that we increase to 5%. Maybe that works for you. You think 5 is large, right? But we cannot. 5 is large, but that's a trade-off, right? We trade off. We want the type 1 error to be small, so the trade-off is that the other one is gonna be large. Maybe that's acceptable for you. Or maybe if you want to increase that to be like, we want to decrease that to be 0.0001%. Right? Maybe that works for you, but that the other one might blow up to, let's say, 70%. Like that's possible. If we don't want anyone to be dead, like we have to spend resources on every single person who comes into the hospital, and that means maybe most of the time we are gonna treat dead people and waste resources. So you have to decide which one you want to minimize. You want that one to be, you can only minimize one. You cannot minimize both at the same time. If you change one value, the other one will increase, just like you have a seesaw. If you increase that, that's going to be decrease, and the other way around, right? So that's again, that's not math. That's kind of like the usual decision-making procedure that you will encounter in life, and of course, usually in statistics. From this set of sample, what should we decide? From this, from the surveys, should we increase or decrease the revenue? From this result of, I don't know, questionnaires, should we target more teenagers or not? Something like that. So that's the non-math part. Right. So let's take a break and continue to the next clip for the p-value.